Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Selamat siang, Bapak, Ibu, dan teman-teman semua. Selamat siang juga, Prof.
Selamat siang.
Semoga dalam keadaan sehat dan berbahagia selalu untuk kita semua. Sebelumnya, terima kasih atas kehadiran Bapak, Ibu, dan teman-teman semua pada acara ini. Pada siang hari ini, insya Allah, kita akan melaksanakan workshop atau webinar seri ketiga dari WCP 2022 dengan tema Electrical Drive System Simulation using MATLAB Simulink yang akan diisi oleh Prof. Nik Rumzi Nik Idris dari Universiti Teknologi Malaysia. Sebelum kita mulai acara ini, marilah kita buka acara ini dengan sama-sama membaca Bismillah. Bismillahirrahmanirrahim.
Bismillah.
Sebelumnya perkenalkan, saya Hendril Satrian Purnama, di sini sebagai moderator yang akan memandu acara pada siang hari ini. Sebelum kita mulai acara ini, maka izinkan saya membacakan sedikit biografi dari Prof. Nik Rumzi sebagai narasumber kita pada siang hari ini. Profesor Dr. Nik Rumzi Nik Idris merupakan profesor aktif di Universiti Teknologi Malaysia pada bidang Control and Power Drive System. Beliau juga merupakan kepala dari Power Electronics and Drive Research Group di bawah UTM ya. Beliau menyelesaikan S1 di University of Wollongong, Australia, kemudian master di Bradford University, UK, dan Ph.D. di Universiti Teknologi Malaysia. Selain itu, beliau juga pernah menjadi pembimbing dari S3 Pak Tole Sutikno Ph.D. Selaku penanggung jawab dari workshop series ini. Di Scopus sendiri, beliau memiliki lebih dari 170 artikel dengan 2.867 citasi dan H-index 25. Baiklah. Mungkin itu saja sekilas profil dari Prof. Nik yang bisa saya sampaikan. Untuk mempersingkat waktu, maka langsung saja kita ke acara inti, yaitu penyampaian materi yang akan disampaikan oleh beliau yang terhormat Prof. Nik Rumzi Nik Idris. Tak lupa mengingatkan nanti teman-teman untuk di akhir sesi kita akan ada sesi tanya jawab juga ya. Baiklah, mungkin pada Prof. Nik, waktu dan tempat saya persilahkan.
Oke, terima kasih Pak Hendril. Pak Hendril ya?
Ya, Prof.
Pak Tole ada sini?
Pak Tole ada, Prof.
Oke, terima kasih ya Pak. Saya akan cuba sampaikan apa yang saya mampulah. Sebenarnya ini adalah invitasi ataupun invitation daripada Pak Tole Sutikno untuk saya kongsikan apa yang saya tahu sedikit berkenaan dengan electrical drives dan simulation system. Ya, boleh saya share screen ya?
Boleh.
Okay. Right, ya. Oke. Boleh nampak ya?
Sudah, Prof.
Sekejap, saya mana? Oke, alright. Oke, boleh nampak ya dan boleh dengar ya?
Boleh,
Prof.
Oke, nama saya Nik Rumzi daripada Power Electronic Drive Research Group. Saya boleh faham ya kalau saya cakap bahasa Malaysia?
Insya Allah boleh.
Bisa ya, bisa. Saya cuba-cubalah bahasa Indonesia. Saya memang tak pandai. Okey, dan campur dengan bahasa Inggeris sikit-sikit lah ya. Sebab istilah-istilah tu kadang-kadang kita kena gunakan bahasa Inggeris. Alright. Daripada Fakulti Kejuruteraan Elektrik, sekarang dia dah tukar semula kepada fakulti. Dulu dia sekolah sekejap. Sekolah Kejuruteraan Elektrik, sekarang dah kembali semula kepada Fakulti Kejuruteraan Elektrik, Universiti Teknologi Malaysia. Okey. Lebih kurang apa yang saya ingin sampaikan kontennya ialah apa itu electrical drives. Sebab sebelum kita melakukan apa-apa simulasi tak kira apa sistemnya, kita kena terlebih dahulu memahami sistemnya dahulu. Jadi saya akan terangkan sedikit fundamental concepts ataupun basics fundamental of electrical drive. Apakah itu electrical drive dan juga apakah fundamental yang perlu diketahui untuk kita sebelum melakukan simulasi. Kemudian saya akan tunjukkan beberapa contoh simulasi sistem electrical drive, iaitu hoist system, electric vehicle, macam mana kita gunakan MATLAB Simulink untuk mereka bentuk ataupun design controller untuk DC motor drives. Kemudian saya akan tunjuk sedikit on the induction motor drive performance, high performance of induction motor drive system, iaitu cuma saya akan ambil contoh field oriented control sahaja. Ada banyak lagi lah jenisnya, cuma saya akan lebih fokus kepada field oriented control, lebih kepada rotor flux. Dan file ini saya akan bagikan Simulink file, saya akan tunjukkan pada slide. Kemudian mungkin selepas ini saya boleh bagikan pada Pak Tole ataupun siapa saja, untuk kalau siapa yang berminat boleh tengoklah Simulink file yang saya gunakan. Saya akan gunakan saya develop dia punya Simulink file SLX tu menggunakan MATLAB release 2021B. Jadi kalau nak guna Simulink filenya nanti, bila saya paskan nanti, kena at least 2021B lah ataupun ke atas release-nya. Okey, kita mulakan dengan apa itu electrical drive. Drive secara umumnya is sistem yang kita gunakan untuk melakukan specific task, to perform some specific tasks such as move the loads and object and so on. Dan to do that task, we have to have a prime movers lah, because that involves mechanical punya energy. Jadi kita kena ada prime mover, and electrical drives is when we use the electric motors as the prime movers to perform this specific task. Okay. Jadi pergerakan motornya tak semestinya rotational, ia mestinya boleh jadi juga motornya ataupun mesinnya pergerakannya ialah translational. Tapi dalam slide ini saya lebih fokus kepada rotational motion lah, untuk motor. Tapi loadnya tak semestinya translational, tak semestinya rotational. Ia boleh jadi bergerak secara translational ataupun bergerak secara mendata. Okey, kalau ada nak tanya soalan, saya boleh ganggulah. Tengah-tengah saya buat presentation pun, kalau ada nak tanya soalan pun tak ada masalah kot. Kalau apa yang kurang jelas, silakan. Terlebih dahulu kita just lihat dia punya background of electrical drive. Lebih kurang 50% daripada electrical energy digunakan dalam electrical drive dalam dunia ini. Saya selebih pun sekarang. Dan electrical drive ni dia boleh dibagikan, can be either classified as a fixed speed or variable speed. Tapi the trend is now lebih kepada variable speed lah, walaupun sekarang ini kalau dikira dia punya application ini banyak pada constant speed, tapi ke arah lebih kepada variable speed, yang semakin berkembang lah. Dia punya advantages-nya kita semua tahulah, just list a few, which ada banyak lagi lah yang mungkin kita boleh fikirkan, which is clean, quiet, efficient, source of energy easily transported by just cables, and then they're available in wide range of power from milliwatt up to megawatt, adaptable to a variety of operation conditions, flexible, can be configured to any conditions, rated torque available instantaneously, tak perlu kita panaskan ataupun warm up sistem. Terus kita boleh startkan dengan terus kepada rated torque, berbanding dengan jenis drives yang lain seperti diesel, hydraulic system dan sebagainya. Itu adalah antara kebaikan electrical drive. Kalau kita lihat dari segi penggunaan energinya pun, ini untuk justifikan yang 50% itulah. Ini saya ambil daripada website di Energy Information Administration, kalau kita lihat dari segi sektornya, industrial, commercial dan juga residential, ya. Kalau kita lihat dari segi industrialnya ataupun manufacturing punya sektor, lebih kurang separuh adalah machine drives, ya, yang selebihnya process and boiler heating, facility cooling, heating and ventilation, which also termasuk electrical drive juga, ya, compressor dan sebagainya, electrochemical process dan sebagainya. Kemudian kalau kita lihat dari segi residentialnya, terutamanya dari segi space cooling menggunakan compressor, electrical drives, space heating tidak menggunakan electrical drive, refrigerators, ya, menggunakan compressor, electrical drive, ya. Dan dari segi commercialnya juga kita boleh lihat refrigeration, space cooling, computers and equipment, some of them are using electrical drive. So boleh dikatakan, boleh dianggarkan lebih daripada 50% lah, ya, electrical energy usage di dalam dunia ini bergantung pada drive. Bermakna untuk kalau kita boleh improvekan efficiency of the electrical drive ni sedikit sahaja pun, ia adalah significant energy lah, ya, disebabkan oleh huge contribution ataupun amount of energy used for electrical drive. Walaupun efisiensinya bertambah sedikit, namun dia punya contribution to the energy saving is huge. Jadi typical electrical drive-nya yang kita akan lihat nanti ialah seperti yang saya tunjukkan di sini, dia ada power electronics, input power, motor, contoh yang setuju adalah 3-phase dan juga load, ya. Power electronic biasanya dikawal oleh controller dan kita akan ada reference lah, ya, reference torque ataupun speed bergantung kepada apa yang kita nak kawalkan. Kita kenakan kepada controller which will generate this power electronic converters. Ini yang saya tunjuk modern, ya, modern electrical drive yang menggunakan power electronics lah untuk kawalan. Optionalnya ataupun kebanyakan case-nya kita perlukan feedback lah, ya, untuk memastikan apa yang kita kawal itu tidak berubah dengan beban ataupun load, ya, ataupun dengan perubahan pada input power ataupun beban ataupun perubahan parameters yang lain, outputnya kekal seperti yang kita kehendaki. Dengan itu kita perlu ada feedback sistem untuk mengawal, untuk menukar switching signal yang kita kenakan kepada power electronics to maintain our desired reference, sama ada speed, torque ataupun position, ya. Jadi kita boleh lihatlah dia punya sistemnya, electrical drive ni is interdisciplinary. It involves the various discipline, mechanical and engineering disciplines, microcontroller, microprocessor, electronics dan sebagainya. Dan the power electronic base electrical drive itself is very small, efficient and flexible kalau kita compare dengan traditional punya electrical drive systems sebelum power electronics converters diperkenalkan, ya. Sedikit very briefly, quickly on elements of electrical drive kat sini. Configurations power electronics converters, ya, bergantung kepada sources available yang kita nak gunakan, sama ada AC ataupun DC, dan kebiasaannya adalah unregulated sources. Dan performance yang kita mahukan daripada electrical drive perlukan braking ataupun tidak, memerlukan response yang bagus, yang accurate, yang pantas, dan juga ratings, ya. Jadi faktor-faktor ini, these factors will determine the type of power electronic converters yang kita akan gunakan, ya. Sebagai contohnya, kalau saya nak control 3-phase motor drive, 3-phase induction motor misalnya, di sini dan saya ada 3-phase sources. Jadi power electronic converters yang saya perlu gunakan ialah AC-DC conversion dahulu untuk menukarkan daripada AC kepada DC, kemudian daripada DC saya tukarkan kepada AC, ya. Dan di tengah-tengah ini ialah yang kita namakan sebagai crowbar circuit untuk melepas, untuk to release the braking energy yang biasanya kita simpan pada capacitor, ya. Sebab this diode rectifier di sini dia tidak boleh, is a unidirectional power flow. Powernya tak boleh masuk semula kepada supply. Apabila berlaku breaking di sini, ya, power tak boleh masuk, jadi kita terpaksa dump the excess kinetic energy semasa breaking, motor braking kepada capacitor, dan seterusnya this crowbar circuit has to release the excess energy if the voltage across the capacitor reaches certain limits. Kita akan tengok lagi contohnya selepas ini. Alright, kalau dari segi controllernya saya boleh bagikan kepada sama ada DC drive ataupun AC drive. Kalau DC drive biasanya very simple, kita boleh implement menggunakan analog circuit ataupun discrete digital circuit ataupun microprocessor controllers. Kalau AC-nya sama ada kita gunakan scalar control ataupun vector control. Scalar control ni dia punya performance-nya adalah tidak berapa bagus. Application-nya contohnya ialah pada fan, compressors dan sebagainya. Kalau kita perlukan performance yang bagus untuk electric vehicle, misalnya untuk elevator system, lift, ya, high performance machine tools dan sebagainya, biasanya kita terpaksa gunakan vector control, dan controllernya, implementationnya agak kompleks lah, ya. Namun kebaikan AC drive ni jika dibandingkan dengan DC drive is on the machine itself, ya. AC drive lebih murah, lebih robust dan sebagainya, whereas DC drive ni walaupun kontrolnya simple tetapi dari segi motornya agak expensive dan juga berat dan sebagainya, ya, ada limitations. Dari segi sensornya pula, kebiasaannya kita akan sense the voltage dan juga current lah, ya, sama ada phase currents untuk three phase systems, AC systems ataupun DC link voltage, kita sense DC link voltage untuk tujuan control dan juga protection, ya. Dan juga kita perlukan torque information, kita boleh gunakan torque sensor dan juga speed sensor untuk tujuan feedback, ya, untuk tujuan feedback untuk kita kawal torque ataupun speed. Tapi trendnya sekarang is we can see that the trend is not for us to use the mechanical torque sensor ataupun rotor speed as to obtain the torque and the speed informations, but rather to use the observers, which are basically software, ya, daripada voltage dan current itu kita boleh construct menggunakan observer untuk dapatkan estimated rotor speed dan juga torque, which what we call, kalau kita estimate rotor speed di sini dia panggil speed sensorless drive lah, di mana kita tak perlu install the speed sensor, mechanical speed sensor, kita just estimate the speed from the menggunakan observers, ataupun torque, kita tak perlu gunakan torque, we can always estimate the torque from the currents and the voltage that we sense, ya. Ini trend yang sekarang dipakai lah. Secara ringkasnya saya nak summarizekan dia punya timeline untuk drive system ni sebelum power electronics diperkenalkan, iaitu sebelum tahun 1958 the first SCR introduced. High performance applications terpaksa menggunakan DC drive, sebab pada masa itu kita tak ada sumber ataupun source untuk variable frequency dan juga variable voltage AC untuk mengawal AC motor, ya. Tapi setelah power electronics direka, seterusnya inverter direka cipta, then we can see that some of the after the inventions of the power electronic converters, kita boleh lihat sebahagian daripada applications yang memerlukan medium to low performance boleh menggunakan AC motor, tapi masih lagi high performance applications masih lagi dominated ataupun didominasikan oleh DC motor, ya. Not until 1970s, around that time, then what we call the FOC, field oriented control, yang akan saya bincangkan nanti, diperkenalkan, di mana performance of AC motor ini lebih menyamai dengan performance of DC motor. Sebelum ini kita tak boleh nak kawal AC motor sama seperti DC motor, tapi setelah FOC, field oriented control, kaedah kawalan diperkenalkan dalam tahun 1970-an, FOC mula diguna pakai dalam high performance application system, terutamanya bermula dalam tahun 1980-an, ya, di mana ia mula dikomersialiskan. Kemudian dalam tahun 1986 direct torque control, another high performance method, was introduced. And then not until 1996 the first commercialized DTC, direct torque control, tapi saya tak akan bincangkan dalam presentation ini, digunakan. Dan selepas itu kita lihat penggunaan dalam high performance applications ini dikongsi di antara FOC dan DTC. Jarang sekali kita lihat penggunaan high performance applications drive di mana perlu precise control for torque and speed and position menggunakan DC motor sekarang ini ya. Kebanyakannya menggunakan AC motor. Dan kebelakangan ini kita lihat satu lagi kaedah teknik yang agak baru, which is based on model predictive control ya, what we call the predictive torque control. Dalam tahun 2010 macam itu diperkenalkan, dan research ke arah itu semakin berkembang lah ya, menggunakan model predictive control ya, ataupun kita kenal sebagai PTC ya. So FOC, DTC, and then now we have also PTC for the high performance applications. Alright, so fundamental of electrical drives, okay. Saya mulakan dengan the most basic Newton's second law of motion untuk translational motion, mengatakan bahawa the net force suggests considering the one directional motion ataupun force sahaja ya, pada satu direction x sahaja, the force and the velocity can be a vector, but we're just considering in just one directional motion. The net force of the force acting on a body, as we all know, is equals to the rate of change of the momentum, which is m times v. Tapi kebiasaannya m adalah constant, jadi kita ketahui umum ya, F, which is the net force, is equals to ma, where mass is the mass of the body, right? So it is the first order differential equations for speed, second order differential equations for displacement. But as I have mentioned before, the motor itself, the electrical motors is based on the rotational motion rather than translational motion. So we can readily apply the same Newton's equations here to a rotational system, but instead of force, it becomes torque, and instead of m, it is now the j, which is the moment of inertia of the system, and instead of v, velocity, it is angular velocity omega. Okay, so the same equations apply. Te minus TL is the load torque, is equals to the rate of change of the angular momentum, and most likely the j is going to be constant. In some applications j can vary as well, tapi kita cuma consider j yang constant saja. So we can take out j from the derivative. So we can have a first order or second order differential equations based on the accelerations or based on the angular positions ataupun angle ataupun velocity ya, angular velocity omega m ya. Jadi equation ini kita akan banyak gunakan ya. Jadi sistemnya ialah simple saja, kita ada motor, electrical torque, dan electrical torque dihasilkan oleh motor, dan load torque yang dihasilkan oleh load, dan motor dan juga load itu bergerak pada arah torque, electrical torque ya. So that system has a total inertia, moment of inertia of j, combining both and load. Then this system can be represented by this equation here. Okay, so we'll be using these equations later when we describe, when we want to design the controllers and so on. Jadi kalau saya multiply the equations with the speed, then I will end up with the power. Yeah, the torque times the speed, angular speed. We have a power, which is the driving power, the load power, and this is basically the change in the kinetic energy, right? So whenever there is a difference between the driving power and the load power, then there will be change in the kinetic energy. In other words, at a constant speed, there is no change in the kinetic energy, but when there is a change in speed, either the motor is accelerating or the load is accelerating or decelerating, then there will be change in the kinetic energy, right? And that change is basically equals to the difference of the energy of the driving power and the load power, okay? Which are, if we look at the equations, bermaknanya a step change in the speed require an infinite driving power lah, yeah? Which is the reason why you cannot have a step change in the speed, which is similar. A rule applies, for example, in the capacitors RC circuit, for example, you cannot have a step change in the voltage across the capacitor. It has to be continuous. Yeah. So the same thing applies here. You cannot have a step change in the speed. The speed has to be continuous. Otherwise, it will require an infinite amount of energy or power to do that. Kalau kita integrate the power, we know we'll get the energy. So if you integrate the drive power, the load power, and then you get the driving energy, the load energy, as well as the kinetic energy. Okay. So again, the kinetic energy stored in the rotating system is given by half of J times omega squared. So any change in the speed will result in change in the kinetic energy stored, which means that kalau kita reduction in the speed, meaning that the kinetic energy will change, and therefore that kinetic energy has to be converted to other form, which means that it will be converted to electrical during the electrical braking, for example. Yeah, we'll talk about that more later. And then another fundamental thing that you should know is the quadrant of operations, which is normally biasa kita dengar lah dalam electrical drive, quadrant of operations. As far as the converter is concerned, the quadrant of operation is defined by the voltage and the current. Ya, kalau dari segi motornya pula, quadrant of operation is defined by the angular speed and the torque. Okay, so electrical machines biasanya can operate in all quadrants. Maknanya the torque can be reversed and the speed can reverse as well. But not all power converters can do that. Yeah. Sebahagian power converters cannot operate in the second quadrant, or even third or the fourth quadrant, can only operate in the single quadrant. Some converters can only operate in the first and the second quadrant, so on. So in order for the drive system to be operable in all quadrants, then both the power converters and the electrical machines has to be able to operate in all quadrants. Yeah. Sebaik saya ambil contohnya ialah kalau kita lihat dari segi motor operations, ya. Kalau saya define the positive speed to be in the counterclockwise direction shown here, yeah, positive speed here, and then the positive torque is going to be in the same directions as the positive speed. So the second quadrant here, in which the torque is negative, is where the torque is opposing the speed. We have a braking mode here. Okay, kalau kita operate in the third quadrant, we have first, second, and third quadrant. Here we have the speed and the torque in the same directions, but in the opposite as compared to the first quadrant. Then meaning that the motor here is the machines is operating as a motor, but in the reverse directions. And then we have the reverse braking mode, where the torque generated by the motor is opposing the speed of the motor, which is in the reverse directions. Yeah. We call it quadrant forward motoring, forward braking, reverse motoring, and reverse braking. Yeah. So in order to shift from these quadrants, it has to be, you cannot just simply jump from 1 to 3. It has to go through 1, 2, 3, and then to go back to 1, for example, you have to brake reverse braking first, and then from there you go to the forward braking. Okay, so the change from one quadrant to another has to be sequential 1, 2, 3, 4, 1, 2, 3, 4. Okay. Contohnya, saya bagi contohnya ialah kalau yang saya tunjukkan tadi, kalau electrical drive AC motor di sini, this AC-DC conversion is capable of bidirectional power flow. Ya. Dia boleh pergi positif, dia boleh pergi daripada electrical kepada mechanical, dan juga boleh kembali semula. Bila kita brake di sini, the kinetic energy akan ditukar kepada electrical. But however, this diode converter here is only unidirectional, which can only flow in one direction because of the unidirectional characteristics of the device yang kita gunakan, diode. So the excess energy during the braking will be dumped to the capacitor here, which I mentioned earlier. Jadi contohnya sekarang, kalau the braking is still electrical, we call it dynamic braking, but it is not converted back to the electrical, to the supply here, but rather it is dumped here. So we have to release the excess energy by using the crowbar here, by sensing the voltage of across the capacitor. So this is a typical industrial drive system which uses which uses the AC motor drive, AC motor for example. Okay, kalau kita nak supaya the excess energy can be recovered back to the supply here, then we have to change this AC to DC conversion front end here to a switching rectifier, which uses the transistors rather than the diode, so that we can control the power flow from the in a bidirectional way, either from left to right or right to left. Okay, but it is going to be more expensive lah, yeah, when we use the switching devices, the transistor rather than the diode. So it depends on the application. Kalau your application, for example, does not require regular braking, then it is not worth to install that expensive switching rectifier. More economical or more practical to use the diode rectifier. Okay, so it depends on the applications. As I said, as I mentioned before, the selections of the converters will depend on your applications. Just to give an example, okay. And another thing is that the flow of the as I mentioned before, dia punya motion of the machines yang kita akan discuss is going to be rotational, but the load does not necessarily have to be rotating. For example, electric vehicle, the load itself, which is the vehicle, is moving in a translational motion. The elevator systems is moving in the translational motion. The conveyor belt system, where the load is in the translational motion, but the motor, which is the prime mover, is a rotational machines. So we have to relate this translational and the rotational motion, and we do that by just a very simple physics yang kita belajar semasa di sekolah menengah dahulu ataupun secondary school dahulu, ya. Relations between the torque and the speed, the torque and the force, and the angular speed omega and the translational speed, yeah. If we use the Newton's first motion of equations of motions, where the net force acting on this body, Fe minus Fl, is equals to m dv dt, then if we use the relationship between the torque and the force, yeah, the torque here and the force here, which relates via the radius of this pulley here, okay, as well as on the load side here, Fl, yeah, force dengan torque, yeah, which is also related by that pulley, and the translation velocity V and the angular velocity is related also via that radius. Then kalau saya substitute this Fe, F and V into these equations, then I will end up with these equations here, which is very important because that will basically gives you the equivalent moment of inertia of the translational motion system as seen by the rotational system. Okay, maknanya rotational system will see an equivalent moment of inertia, which is of a body which is moving in a translational motion, and that equivalent J is basically depends on the radius of the pulley yang kita gunakan di sini. Yeah. Another typical drive system will typically consist of gear systems. Okay, because we want to reduce. Typically, we want to reduce the speed of the motor. Yeah, so but the size of the motor for the same power rating, the size of the motor will be much smaller, which means that more economical if the speed is large. Okay, compared to the same power ratings of a motor with a smaller, with a slower speed. Okay, so in order to have a more compact motor, then the motor has to be running at higher speed. But in most of the cases, we don't want the motion to be that high speed, so we have to use the gear system in order to reduce the speed of the motor. Ya, seperti yang saya tunjukkan di sini. We have a motor here which is coupled to the load, and then we use a gear system here to reduce the speed, which is coupled to a different load which is rotating at a slower speed, obviously. Yeah. Sebab the gear system here, the number of gear here is less than compared to the number of gear system here. Okay, or you can also relate that to the radius R1 to the radius R2 here. Okay, so how do we, in order to apply the equations that we have developed or we have seen before, which is TE minus TL equals to J d omega dt, then the system has to be as simple as this, which means that we have to somehow transform that system with gear into an equivalent system which does not have gear. Okay, so how do we obtain the equivalent system? We can use that by using the principle of conservation of energy, which I'm not going to show here, and as well as the principle of conservation of power. And then we'll finally come out with the equivalent moment of inertia, which is given by that, where J1 is the moment of inertia on one side of the gear system, and J2 is the moment of inertia of the load on the other side of the gear system. A is the gear ratio, N1 over N2, or we can also take the speed ratio, N1 over omega 1 over omega 2 over omega 1, or we can also take the radius, yeah, on R1 over R2. Okay, the radius of the gear. Okay, which means that now our complex system, which consists of gear, can be represented by a simple system which has a motor which is coupled to the load, and then we can use these equations to describe or to perform the analysis on the system. All right. Sebelum kita look at on several examples, let's look at on another fundamental concept that we need to understand, which is the torque speed characteristics. When we talk about the electrical drives, basically we are dealing with not only electrical system but also mechanical. Okay, and kalau dalam electrical engineering, when we characterize a device by looking at the voltage and the current relationship, but for mechanical systems, which in this case the drive system itself, which is the load and the motor, a mechanical system is characterized by its torque and speed. It's like a voltage and the current in the electrical system lah. Kalau kita nak lihat characteristics of a capacitor, we look at the characteristics of the voltage and the current. Of a diode, we look at the characteristics of the voltage and the current. Kalau untuk motor, various type of motor, we look at the relationship between the speed and the torque characteristics. Yeah. Kalau induction motor misalnya, it has a characteristic which is something like that, which I'm sure some of you have. Kan kita sudah tahulah ya, characteristics of the motor, characteristics of a synchronous machines, constant speed. Okay. And then we have a separately excited or shunt DC machines, which is characterized by the green, and if it is a series DC machines, then we have a constant power characteristics. These machines can be changed, the characteristics can be changed by at will, bermaknanya kita boleh tukar the characteristic to any characteristic that we want by controlling the voltage and the current of the motor, okay, by using the power electronic converters. The load itself, because when we talk about electrical drive, then it is basically the interactions between the load and the motor, yeah, electrical motors. So we have to know as well the characteristics of the load, the torque speed characteristics of the load, which can be divided into two types. Load, which is a passive load, we call it passive load, which is basically caused by the frictional torque. Yeah, ada beberapa jenis friction yang ada pada electrical, any mechanical rotating systems, Coulomb, viscous frictions, and also friction due to the turbulent flow. Basically all this friction existed dalam electrical motor, tapi depending on the load, one or two will be dominant. Ya, contohnya dalam fan system misalnya ataupun compressor, then the one which is going to be dominant is the one which is the friction which is due to the turbulent flow. Okay, in the some traction drive system, Coulomb friction is dominant as well. Okay, Coulomb friction does not depend on the speed. Okay, it is constant, but it only exists when there is a motion. Okay, this passive load of frictional torque only existed when there is motion. That is the reason why we call it as a passive load. Yeah, kalau tak ada motion, maknanya tak ada torque, and this passive torque typically normally will always be opposed opposing the motion, which means that we will always be opposing the electrical torque produced by the motor. Another type of load is what we call the active load. Ya, active load ni bukan disebabkan oleh friction, tapi contoh yang a good example is the gravitational pull, and it does not depend on the speed. Okay, whether you are moving in the forward or reverse speed, the gravitational torque or the gravitational load is always equal, the same, right? Sebagai contohnya, kalau kita lihat on vehicle drive system, ya, kalau kita bergerak pada inclined road with an angle alpha here, then if we resolve the gravitational pull there, mg, into two components, which is normal to the surface of the road as well as parallel to the surface of the road, then the one which is pulling this vehicle down, which is FL, is contributing to this gravitational torque. Okay, and depending on the inclinations of the road, this gravitational pull, which is pulling that vehicle downhill, is given by RGM sine alpha. Okay, whereas alpha is the inclination of the road. Yeah, jadi kalau elevator system, for example, will have a gravitational pull, which is an active load as well. Yeah, another example. Okay, jadi kita ada dua load characteristics and the motor characteristics, torque speed characteristics. Okay, depending from the torque equations that we have seen before, TE minus TL equals to J d omega dt, which means that under steady state, then the speed is basically, the rate of change of speed is 0, which means that under steady state, then TE is equals to TL. So if we have the motor characteristic, for example, is shown here, then we have the load characteristic, which is the turbulence flow. Due to the turbulence flow, then the steady state speed is going to be the interactions or the intersection point between the motor and the load, which is shown here. Bermakna kalau saya nak tukar dia punya steady state speed, then I can just change the characteristics of the motor, okay, by using the power electronic converters, for example. Okay, so kita tak boleh buat apa on the load, because the load depends on the type of load that we're using. But what we can do is we can change the characteristics of the motor so that we can change the speed. So this is the concept of variable speed that we have here, by changing the characteristics of the motor using the power electronics converters. So to look at on the ratings of the motors and the converters, just to summarize on the characteristics that we've seen just now, and the equations that we've seen just now. For fast acceleration, we require that the motor torque has to be much larger than the load torque. Again, this is based on the TE minus TL. The load is equals to J d omega dt. Yeah, so this is the acceleration there, meaning that if you want a faster acceleration, when you change the speed, then you have to provide a very large electrical torque compared to the load torque here, so that the motor will accelerate to a new speed, right? And then once it reaches the new speed, then we balance again the electrical torque and the motor torque and the load torque, so that the speed, the rate of change of the speed will goes to 0 again. For example, a good example would be when you are driving a car, for example. Yeah, you press, when we are traveling at a constant speed, we press the pedal, which is basically the torque demand, at a constant pressure lah. Yeah, but when we want to overtake a car, for example, then we press further the acceleration pedal, which means that we are requesting more torque from the motor or from the engine, right, in order to accelerate. So if TE is larger than the load torque, then d omega dt will become positive, which means that the motor will accelerate. Once we reach the speed that we want, then we ease the accelerator pedal to balance the load torque and the motor torque, so that we have a constant speed again. Okay, So the transient torque limit can be several times motor torque limit because of the largest thermal capacity of the machines. Okay, the machines itself typically will have a very large thermal capacity. In other words, it will take some time before the machines can be damaged at a higher temperature. Yeah, because of the large thermal time constant, will take some time before the temperature is reached to a maximum temperature. On the other hand, the switching devices yang kita gunakan dalam power converter will have a very small thermal capacity. Ya, maknanya kita tak boleh go beyond the rated values of the current of these devices, because the moment we go beyond the rated current values, then the devices will immediately heats up and it will immediately damage the devices. Yeah, sebab apa? Sebab the devices will have a much smaller thermal capacity compared to the machines. So it is allowable for us to go beyond the rated value of the machines, of the motor, several seconds before the maximum temperature is reached, but it is not allowed at all for us to go beyond the ratings of the devices, okay, because of the small capacity of the devices. So if you look at the which means that when we design the converter, we have to make sure that the converter can operate larger up to what we call the transient limits of the torque speed characteristics. Yeah, kalau kita lihat the torque speed characteristics envelope, where this is the area in which we are allowed to operate continuously. Yeah, this torque limit is basically limited by the current of the motor. Okay, if we want to operate the motor continuously, we cannot go beyond this torque limit. Okay, and then this is the limit of the power. Okay, of the power. If we go beyond the base speed here, then we have to reduce the torque capability. And then we have a limit of the speed. All right, so this is the continuous limit of the motor. Kalau saya nak accelerate, I can go beyond the torque limit for several seconds, all right, because it will take some time before the temperature of the motor to reach the maximum temperature. So we have another limit, what we call the transient limit, yeah, which can go beyond the rated values of the motor, but we cannot operate the motor in this region continuously, only momentarily. Okay, during acceleration, you can go beyond that rated values of the torque of the motor to get a faster acceleration. But you cannot operate this continuously. So this transient limit is basically the limit which is set by the capability of the device, because you cannot go beyond that, right? Jadi maknanya device kita biasanya kita set kat sini lah, capability of the device, the maximum current, okay, and the power and so on. We have to set that depending on the device, because if you go beyond that, then the device will damage. And in order to operate continuously, you have to operate within this continuous limit. All right. So that is basically the how we determine the ratings and the of the motors and the converters. Yeah. All right. So let's look at on the second part is I'm going to go through the various examples of how we use MATLAB Simulink to simulate, to design a system and to analyze the system. Right? I'm just going to give you a few examples sahaja, which is a hoist system, the electric vehicles, and the how to design the controller using the MATLAB Simulink, and then how to simulate the high performance motor drive, AC motor drives, which is the field oriented control. Okay, so basically that will be 3 parts here, which is the simulating the hoist system, is basically used to obtain the initial ratings of the motor. Okay, from these simulations we can obtain the initial ratings of the motor. What is the power rating, what is the maximum speed rating, depending on the requirements of the system. Kita akan lihat for the hoist system, which is, for example, elevator system ataupun lift system. And then also we're going to look at on the electric vehicle systems. And we are going to use two Simulink as well as Simscape. Okay, Simulink, as we all know, saya rasa kita semua tahu lah, is a graphical user interface to MATLAB. Simscape also is a graphical user interface to MATLAB, which is part of the libraries offered in Simulink. But dia punya method of simulation is slightly different. We'll see that later on. Okay, after this, I will show you what is the difference between Simulink and Simscape. And then we're going to look at on how we can use MATLAB to design the controllers for DC drive, basically, right? I'm going to just give you one example of the cascaded control structure of the DC motor drive, how to control the torque and the speed of the DC motor drive. And then finally, we're going to look on how the MATLAB and Simulink can be used to simulate, design, as well to analyze the high performance induction motor drive, which is a very highly non-linear system. This is basically a linear system. This is basically a non-linear system which involves mechanical and electrical domains. All right. This is basically a non-linear system, which involves power electronics, converters, and the induction motor drives modeling. Right. So as I mentioned earlier, saya akan mungkin kalau sesiapa berminat, saya akan bagilah pada Pak Tole ataupun siapa the corresponding Simulink MATLAB file yang saya akan gunakan dalam contoh yang akan saya tunjukkan di sini. Okay, so we start off with the hoist system. All right, this is example of a system. Hoist, we have a motor here, which is used to lift object A, and we have a counterweight here. B is a counterweight. Dalam elevator system pun macam itulah lebih kurangnya. Cuma dalam sistem ini saya tak ada gear system lah, which means that the motor is directly used to lift the speed of the motor is directly used to lift the carriage A and the counterweight B here. Okay, which is typically applicable dalam high speed elevator system. Dalam high speed elevator system dia tak ada gear system. High speed meaning that the speed is very, very high. So the speed of the motor itself is not converted or is not reduced in order to provide that translational motion of the carriage A and B. Right. Jadi kita tahu kalau kita nak guna Simulink, first we look at the Simulink, how we simulate using Simulink. Simulink. What we need first, we need to develop the mathematical model of the system, and then from the mathematical model, then we use the Simulinks to represent that mathematical model. Okay, so mathematical model di sini kita dah lihat sebelum ni lah on the fundamentals of electrical drives. So the system here involves a translational motion, which is object A and B, and the motor is a rotational motion. Okay, so we have to find the equivalent moment of inertia in order for us to represent this system here with an equivalent system shown here, which is given by the equations. Then we have to find what is the equivalent moment of inertia and what is the equivalent moment of load. Okay, so how do we do that? Equivalent moment of inertia of the system of the equivalent system here is composed of what? Moment inertia of the motor itself, Jm, and then moment inertia of the sheath, which is directly connect to the motor shaft here. And then we have the moment inertia of the translational motion. Remember, kita dah derive tadi, which is basically equals to the mass times the r square, which is the radius, in this case, the radius of the sheath. So this is going to be the equivalent moment of inertia of the system. And then the equivalent load is going to be how do we transform the translational motion, translational force, which is basically the gravitational force here, into a torque. Okay, we just simply multiply the force, the net force, the load, which is the net force on the load is basically, you have to subtract because we have a counterweight here, which is basically is lifting that object A, which is helping in lifting up the object A. And then we have the weight of weight A itself, which is pulling down object A. Okay, so the total net force acting, the load as seen by the shaft here, is going to be the difference between the weight of A and the weight of B. Okay, it happens in the system that A is heavier than B, which means that the net force is going to be pulling down here, which is equivalent of, you know, a load torque in that direction here. Okay, so that equivalent load torque is equals to the force, the net force acting times the radius of the sheath system. So this is the mathematical representations of the system. Okay, the mathematical representations of the system, and then now we will use these mathematical equations to represent the system using Simulink block. So how do we do that? This is how you do it. Okay, just a simple Simulink block here. This is your torque, the final torque that you require. This is the speed profile that we want. Kalau kita, the speed profile of load A, apa dia profile dia, macam mana kita nak accelerate dia naik pada certain velocities and then maintain constant, for example. We provide that profile here. I'll show you that later on in the result. Okay, the profile. And then we have the load torque here. Okay, first, this is the moment. How do we obtain the equivalent moment of inertia? We have Jm, Js, Jm, Js, and then we have the moment, equivalent moment of inertia, Ma, Mb there, times r square, then we add. So this is our J equivalent. Okay, this is our speed, d omega m dt. So if you multiply that, then you will get J d omega dt here. And then this is our load torque, okay, which is M times the gravity, M minus M, Ma minus Mb times the gravity times the radius in order to convert to torque. Okay, so this is the torque. So this is the equivalent load torque. You add that together, T L equivalent, then that is going to be equals to the electrical torque that we need. Okay, so in order to simulate using Simulink of this hoist system, for example, you have to develop the mathematical model first, right? An easier way of simulating, but not necessarily a good way, is to use Simscape. Let's look at on how to use Simscape. In Simscape, you don't need to develop the mathematical model first, which means that you don't have to have a background of how to develop the model, but rather you use the physical components which is available in the Simulink library, interconnect it, and then simulate the system, right? Which means that they are faster because we don't have to develop the mathematical model. We can just use interconnect the physical systems from the library to create the systems that we want to simulate. Okay, bermaknanya kita tak ada physical insight of the system. We don't have the physical insight of the system. Okay? Kalau kita guna Simulink tadi, sebelum kita simulate, we already have a physical insight of what is going to happen, what is the torque requirement, and for a given speed profile, for example. But if you are using Simscape, then you have no idea because you have no equations to describe the system. All right, you just interconnect the system and then you simulate the system. Compared to Simulink method, obviously Simscape is faster. Simscape, by the way, is available in MATLAB, I think, after release 2016, if I'm not mistaken. Okay, before that, we don't have Simscape. After release 2016, then we have Simscape libraries. So it is faster, okay, but because you just interconnect the system. And then there are multiple domains as well. In Simscape, you can have a mechanical domain, you can have a translational domain, you have a translational, you can have rotating domains, you have a electrical domains, you can have a hydraulic system domains, and so on. So, and you can interconnect these domains, which means that you can almost simulate any physical system that you have, as well as as they have the libraries to represent that that physical components. Kalau kita tak ada pun library dalam physical components tak ada dalam library Simscape, we can develop our own physical components. Okay, so using Simscape is very, very powerful and very easier to simulate the system. Let me just show you the same system here to use Simscape. So what happened here is that we use a wheel and axle to interface between the translational domain here, which you can see the color which is in light green here, into a, this is a rotating, sorry, not translating, rotating domain, rotating mechanical domain. Then we have a translating mechanical domain here, which has a different color. Okay, so we use a wheel and axle device to convert between the two domain. Okay, and then once we have that, then we can just simply use the J, the moment of inertia here, to represent the moment of inertia of the motor and the shift, which is connected on this side of the system, which is a rotating domains. Okay, and then we inject the speed here, or we can inject, in this case, we inject the speed here, or we can also inject the torque. Okay, we inject the speed and we can observe what is the torque for a given profile of the speed. On the translating domain, we just inject, we just connect the mesh, the two meshes here, okay, and then the load torque, which is the difference between mesh A and mesh B, okay, which is represented by here, MA minus MB there, times G times gravitational. Then we use the ideal force to inject the force which is acting on the translational motion, okay, which is basically a force. I'm not using any equations here. I'm just using the components here and then changing the values of the mass and the moment of inertia in order to simulate the system, which means that I don't have to have the equations or the physical system or the mathematical equation to describe the system before we actually simulate the system. All right. For example, here shown here, if I have a profile here which shows the required profile that we want, for example, from stationary, and then I want to accelerate A upwards up to a velocity of 2 meters per second, and then maintain a constant speed of 2 meters per second, and then decelerate to 0 speed again. Okay, this is the speed velocity of A there, to 0. Then the torque required, that is required to produce here, can be obtained from the simulation here. Okay, the torque that is needed to accelerate, to maintain a constant speed, and then to decelerate here, which is shown there. Okay, this is the equivalent angular speed of the motor shown here, and this is the position. Obviously, kita naik acceleration, position V, the X position here, basically just X there, is increment, then and then it maintains at a constant positions where the velocity goes back to 0. Okay, these are all obtained from the Simulink or Simscape Simulink files. Okay, and then this is the file that I use to simulate the system. You can, if you are interested, you can then run and see how this system, the hoist system, is simulated using based on that Simscape file. Okay, so let's look at on how we simulate an electric vehicle. Okay, using MATLAB Simulink, right? And again, I'm going to use the Simscape library here to simulate this electric vehicle using the drive line library under Simscape to model the electric vehicle. Before we do that, let's just model the electric vehicle first very quickly. We know that the dynamics equations of the electric vehicle again is governed by the second motion of law, Newton's motion of law. The the net force acting on the car. Okay, this is the tractive force, FTF plus FTR, the front and the rear. If it is a all-wheel drive, if it is a front-wheel drive, then this FTR is basically equals to rear tire is equals to 0. But if you have a four-wheel drive, then we have 4 tires, front and wheel tractive force. Then we have the minus the load here, which is combinations of several resistance there. Okay, which is the aerodynamic drag, the grading resistance, depending on the inclinations of the road. And then we have the rolling resistance of the front tires and rolling resistance of the rear tire. The net force acting on the car which is the tractive force provided by the motor minus the resistance, must be equals to the m, the mass of the vehicle, times the rate of change of the velocity. Okay, so this is how we model in a translational motion. And I'm just considering the longitudinal motion of the car, okay, in one directions of the car for this simulation here. What is the aerodynamic drag? If the car moves in the forward directions here, in that direction, for example, then obviously we have a high pressure at the front of the car and we have a low pressure at the back of the car. This low pressure will drag the car behind. This is what is cause of the aerodynamic, we call the aerodynamic drags, as well as there will be a skin friction between the moving air and the car itself, okay, or the vehicle itself. And the aerodynamic drag can be modeled by this force here, which is equals to half of rho AF, which is the frontal area. CD is a drag coefficient which depends on the shape of the car, okay, and then a velocity of the car. So that is the aerodynamic drag. And then we have the rolling resistance, which is caused by the deformations of the tire, basically. Okay, kalau tire is ideal when it is moving in that directions here, then the normal force is equals to the reaction force here. Okay, reaction force is equals to the normal force moving, which is acting through the same point, which is the center of the tire or the radius here. Okay, center of the tire, tengah-tengah tire lah di sini. Tapi in practice-nya, when the tire moves, it will deform. Okay, because of the deformations of the tire, then the normal force will no longer acting through that center of the tire. Jadi akan ada net normal force which is going to be acting in that directions, which forces the wheel, which produce a moment of wheel, the force which is acting on the wheel, which is going to be in the opposite directions to the motions of the tire. Okay, because of the deformations there, then you have a normal force which is no longer acting through that center of the tire, which is going to produce a force which is going to be in the directions opposing to the motions of the wheel. Jadi depending the rolling resistance force ni bergantung kepada type of material of the tires that we use, as well as the type of the surface of the tire, the surface that the tire is rolling. Contohnya kalau pasir tu, we can see that the deformations of the surface is significant dan rolling resistance is very large, which is the reason why kalau kita nak gerak atas pasir is very difficult, okay, because of the large rolling resistance which is caused by the deformations of the surface of the road. Okay, so that is how we model the rolling resistance. And then finally the grading resistance, again, which I have shown you earlier, which depends on the inclinations of the road and the gravity which is pulling the car downwards, which is given by mg sine theta, sine alpha, where alpha is the inclinations of the road. Combining that, then we have that the total the resistance force there, combining the aerodynamic drag, the grading, and as well as the rolling resistance there. Now, how do we model the electric vehicle? There are different architecture or configurations of electric vehicles. Kalau kita do a conversion, for example, we know that the internal combustion engine vehicle has the internal combustion engine here, which is connected via the clutch to a gearbox system. And then from there, we have a differential gear, which is connected to your wheel, right? The same for the electric vehicle, almost the same system, except that we don't need the multiple gear here, gearbox here, and we don't need a clutch system here, okay? Because we don't have to change the gear. So the electric motor is directly coupled to a single gear system, and then again coupled to a differential gear. The differential here is required because when the car is turning left or right, then the speed of the left and right wheel is going to be different. that difference will be taken care by the differential gear here, all right? So this is the model that we are going to develop, which is based on a simple architecture of the electric vehicle, a simple single motor, onboard motor, the single gear, and a differential gear. Okay, starting from the tractive effort, which is equals to the aerodynamic drag, rolling resistance, and the grading here. And then the drive shaft, the force here is transformed into a, the tractive force there is transformed into a drive shaft, which is the drive shaft which depends on the wheel, radius of the wheel here, okay? Assuming that the drive shaft, the gear has a ratio of 1:1 here, the differential, okay? Which means that the torque developed by the tractive effort required here is just a multiplication of the tractive effort with the radius of the vehicle, right? And then on the motor shaft, which is on the other side of the gear, then we have to convert, in order to convert to the motor torque required, then that drive shaft is multiplied with the gear ratio and then divided with the efficiency of the gear system, right? Efficiency of the gear system, which is typically very close to 1. And the drive, the gear ratio there can also be represented by the difference in the drive shaft speed and the motor speed here. You know, but it is a single, it's a single gear system. Typically, for example, 1 to 10 or 1 to 6, and so on. Okay. So this is the motor resistance. This is not the tractive effort. This is the motor resistance, how we convert the resistive force to a drive shaft resistive torque, and then to a motor torque, which is the equivalent load here. Okay, the equivalent load as seen by the motor shaft. The tractive force, on the other hand, is also converted using the same principle. You convert from the tractive force into a load, into a torque as seen by the drive shaft, depending on the radius of the tire of the wheel, and then from the torque on the drive shaft to the torque of the motor shaft using the gear ratio and the efficiency of the gear here. Okay, and then from there, we can therefore write down or draw the equivalent moment, the equivalent system here. Okay, we have a motor shaft J, and then we have the motor torque, and then we have the motor, which is omega m, and then we have the equivalent resistance there. Okay, here, and then we have the equivalent moment of inertia, which is which is basically roughly equals to the mass of the vehicles times the radius of the wheel square. Okay, once we have that, simplified the electric vehicle into this equivalent system, then we can use this equation here to analyze or to simulate the systems. To look at the power flow, okay, we have a battery, which is a power which is coming from the battery, and then we have the minus the accessories power, for example, the air conditioning system, the lighting system, and so on. And then which becomes the input to the motor. Okay, and then the efficiency of the motor will determine the power of output power of the motor and the controller. Okay, the efficiency of the motor and the controller, and then which will becomes the input to the gear system, and then the output to the gear system will be connected to the wheel. So this is the final power which is available at wheels of the vehicles. Okay. Depending on the efficiency of the motor and the controller, and efficiency of the gear systems, and also minus the accessories power that we use for the vehicle. Okay, so this is the equations. Motor in is equals to the battery power minus the excess power, accessories power, and then output power of the motor equals to times the efficiency of the motor times the input power to the motor, and then the available power at the wheel is equals to the motor power in output power times the efficiency of the gear systems, right? So from there, the output power here can actually calculate the torque required or the current which is drawn from the battery. Okay, so for example, this is the battery model of the battery that we use. We have the internal voltage and the internal resistance of the battery, the terminal voltage of the battery, and then this is the control current source to model the power required by the accessories, the air conditioning system, the lighting system, just simply obtained by dividing the accessories power with the voltage of the battery. Okay, and then the power drawn for the propulsion system is obtained by dividing the motor power, which is obtained from here, okay, with the battery voltage and of course the efficiency of the motor itself. Okay, so this is the current drawn by the motor, which is modeled based on the efficiency of the system, of the controllers, of the converters, of the efficiency of the gear system, and also the battery voltage. All right, so I have developed the model based on that system, and this is the Simulink model of the system. You can actually see that later on from this Simulink file, which I will give you later on if you are interested, to analyze the performance of the vehicle. Okay, all right. To analyze the performance of the vehicle. For example, from there we can look at on how far by changing the parameters of the vehicle, for example, by changing the weight, by changing the battery size, or by inserting a supercapacitor in parallel to that battery model. For example, here I can have another source here to represent a supercapacitor which can be controlled. For example, then I can analyze the performance of the vehicle. Okay. And for example, here I'm using the new European driving cycle and EDC to run the simulations or to run the vehicles, and then to look at on the speed of the vehicle, the distance travel, the motor speed, the torque developed by the motor, and the state of charge of the battery, for example, right? If you go down into this vehicle model here, then this is the block of the vehicle. Okay, it is then further comprised into two parts: the vehicle subsystem and the battery system. Right, the vehicle subsystem here will develop the motor speed, and then based on the motor speed and the electric torque, we can obtain the mechanical power. Okay, and then from the mechanical power, we use the battery model that I've shown you earlier to obtain the various parameters of the battery, which is the battery current, battery voltage, state of charge, and so on. So you can, if you double click to this block, then you can change the efficiencies, the radius of the wheel, the battery, the initial state of charge of the battery, the kilowatt hour of the battery, and so on. You can go on. Based on this file here. So this is the top envelope of the motor, which is basically just the envelope that we have seen earlier. So whatever the torque demand has to be contained within that envelope. Okay, the torque demand there has to be contained within that envelope, which is in which the output will becomes the motor torque. So if you double click to that, I think, yeah, if you double click to that block there, which is the vehicle system, then you can see that it is basically built based using the Simscape driveline, right? I have developed that using the Simscape driveline model. We have 4 wheels here. You can trace that later on. Then we have a differential gear here. We have a gearbox here, all right? And then this is the motor torque here, and this is the vehicle dynamics, which is provided by the driveline. Let me spell it correctly. Driveline libraries, in which you can change the weight of the vehicle, the center of gravity locations, which determines the maximum tractive effort that you can give, and so on and so forth. All right. And then you can also have a different model of tire, in which you can set the rolling resistance of the tire, the radius of the tire, and so on here. This is the model of the battery, which is that part. Okay, the battery subsystem there. which basically just consists of two current sources, as I said before. The first current source here is the to represent the accessories power losses. This is the high voltage battery power pack of the vehicle. And then another current source is obtained by looking at the torque and the speed of the vehicle. Okay, so you divide the torque and the mechanical power depending on the efficiency of the system. Then we obtain the electrical power, and then from the electrical power, we divide it with the battery voltage to get the current of the battery here. Okay, or the current which is used to propel the vehicle here. Okay, so we have the accessories current, and we have the current which is used to develop the torque to propel the vehicles. And from the battery model, then we can observe the state of charge, the current of the battery and the voltage of the battery. Okay, and then what I did here is I just simply stopped the simulation once the battery state of charge, for example, goes down to 25% of the initial state of charge. This is example of the outputs of the simulations using the new European driving cycle. This is the driving cycle, the speed of the vehicle in kilometer per hour, the accelerate and then decelerate, a standard driving cycle for new European driving cycle and EDC. This is the motor speed. Okay, and then this is the this is distance travel by the car in kilometer, and then we have the motor speed, and then we have the motor torque, which is governed by that envelope of the torque there. Okay, the maximum speed of the motor. This is the speed and the torque, and then the maximum torque of the motor. Okay, maximum speed and the maximum torque. That relationship of the torque and the speed is just inversely proportional to 1 over omega. Okay, so this is the state of charge of the battery. So from there we can design we can have the initial design of the vehicle depending on the weight, the size of the battery. Then we can determine what sort of the kilowatt hour is required by the battery in order to achieve a certain travel range, and so on and so forth. And you have a different algorithm for the control for the supercapacitor, which is inserted in parallel to the battery. Then we can also use that in order to design, to have to study the initial, to perform the initial study of the hybrid energy source system, including the supercapacitor, for example. All right, let's look at on how next on how the MATLAB is used to design the controller. Okay, and I'm going to be specific here to design the controller for the DC motor drives. All right, and the structure of the DC motor drive is the cascade structure, which has the outer speed loop here. You have to have a knowledge of a control system in order to be able to appreciate and understand on how to design the controller here with the help of MATLAB here. Okay, and then we have the inner torque loop here. This is the inner torque loop. There, the inner torque loop and the outer speed loop here. There are two controllers that we need to design: the speed controller and the torque controller. And how do we use MATLAB in order to design that? Before we need to design or can design this controller, we have to have the linear model of the system. So this is basically a linear model of the system, transfer functions of the DC motor, which I'm not going to discuss here. But I will show you later on that I have a YouTube videos on this, on how to obtain the model of this DC motor if you are interested, and how to develop the DC-DC converter model, which is just basically a DC gain. Okay, and then this is the model of the system which relates the torque and the speed, which is just depends on the viscous friction constant B and the moment of inertia of the system. All right, So our task is to design the controller, and we are going to use MATLAB to design the controller. How do we do that? So these are the two controllers that we need to design. And like any other control system, the control objective of this system is to have a fast response as possible with minimum overshoot and zero steady state error. And this can all be obtained by using the body plot, and we are going to use body plot in order to design the controllers with the help of MATLAB. Okay, so how do we translate this control requirement, fast response, minimum overshoot, and zero steady state error using the body plot? A fast response meaning that you have to have as large control bandwidth as possible. Okay, and a control bandwidth, a closed loop control bandwidth, is equivalent to the crossover frequency of the open loop plot. Okay, for example, if you plot an open loop transfer functions of the system, then the crossover will represent the closed loop control bandwidth. And in order to have a fast response, we want this crossover frequency to be as high as possible. But we have limitations because we are using power electronics. We are not using the analog power systems. So power electronics have switching frequency, right? And that bandwidth is going to be limited by that switching frequency of the power converters that we use. So the rule of thumb is to have a crossover frequency of the closed loop bandwidth a decade lower than the switching frequency of the converter. For example, if you're using a triangular wave to generate the PWM for your converter, and you are using a 20 kilohertz triangular frequency, then your control bandwidth has to be a decade lower than that, which is 2 kilohertz, for example. Okay, and then how to minimize the overshoot? By having a large phase margin as possible. So in electrical drive, it is typical, or it is good enough to have at least a phase margin of 65 degrees in order to avoid excessive overshoot in the response, right? And again, we can look at the phase margin by looking at the body plot, which can be obtained using MATLAB to design the phase margin of the system. And then zero steady state error is obtained by looking at the DC gain of the system. Okay, by looking at the DC gain of the system, which means that in order to have a zero steady state error, we have to have an infinite DC gain. And that can be taken care by looking at the body plot again. And if you have an integrator, for example, if we are using the PI controller, then most likely if your system type is 1, then you will have an infinite DC gain, which means that your steady state error will basically is equals to 0. So how do we do that? Assuming that we have the model here of the system, first we want to design the controller, the top controller. So what we need to do is we have to remove that speed loop first, and then we remove the torque loop, and then this is basically the open loop transfer functions of the torque, right? So for this particular example, the model of the DC gain is given by these two blocks here, which depends on the DC voltage that you use, as well as the peak of the triangular waveform that you use to generate your PWM using your pulse width modulation. And then this is your PI controller, right? Which is your torque controller there. So this is just a normal control system design. Okay, how do we design that PI controller? We plot these open loop transfer functions, and then from there we select the values of Kp and Ki, suitable values of Kp and Psi, such that we obtain our desired closed loop bandwidth, which again has to be a decade lower than the switching frequency of the triangular pulse width modulation that we use. Okay, so that subsystem is basically just equivalent to that transfer function here, which relates the voltage and the torque here. So this is your torque, this is your input to your torque reference there. This is your PI controller, and from there you can start plotting before you can actually plot the body plot from this open loop transfer function. You have to define where is the input and output. So if you right click the line which there, for example, and then you go to the linear analysis point, then you define that as open loop input, and then this is going to be your open loop output. All right, then you have the input here, and then you have the output here, and then you invoke the analysis by using various tools that we have. For example, you can use the linear analysis tools, or you can use a control system designer tools. Okay, from the Simulink menu, pull down menu, you can invoke the linear analysis or the control system design. This is, for example, the linear analysis tools. If you use a linear analysis tools, then this is the body plot of the open loop transfer functions of the torque loop. Yeah, the open loop transfer function of the torque without the PI controller. Okay, and this is for example, a Windows that is shown if you're using a control system designer tools, which is also available from the MATLAB. So how do we select the KPKI? As I said, it is not a unique way of designing this KPKI, as long as you fulfill the requirements of the bandwidth, which is to obtain the largest bandwidth as possible, limited by the switching frequency of the converter. Okay, and then obtain a phase margin of 65 degrees, and then have a zero steady state error, which means that a large DC gain. Okay. If you look at the transfer functions of the PI controller, okay, and then expand that, you can see that the PI controller is basically composed of three parts. We have a DC gain here, we have a zero, and we have an integrator there. Okay, the way that we select KPKI will determine the locations of the zero here, right? So for a first order system, I typically use zero locations to cancel the pole of the system, right? And then once I've canceled the pole, then I will use KI here to change the DC gain to obtain the required phase margins, as well as the crossover frequency, right? Once we have that top controller design, then we proceed with the speed loop. Okay, so which means that now, for example, for instance, we have already designed this top controller, then we can actually remove this top controller and replace it with just a unity gain. Okay, because we are assuming that the top controller is perfectly designed and such that the speed bandwidth is a decade lower than the torque bandwidth, which means that the gain of the torque loop at the speed bandwidth is equals to 1. So which is conveniently, which is the reason why we can conveniently replace the torque loop with just a unity gain 1 here. Okay, which means that the speed controller KP and KI here is basically just determined by the B and J of the system, moment of inertia and the viscous friction constant of the system. And the bandwidth of the speed has to be a decade lower than the bandwidth of the torque. So if you start with a 20 kilohertz PWM, for example, then the bandwidth of the torque has to be 2 kilohertz. Then the bandwidth of the speed has to be 200 hertz. Okay, just for example, right? Just for example. Step to design the KPKI is similar, which means that you have to fulfill the bandwidth, you have to fulfill the phase margin, and you have to have a large as possible DC gain in order to obtain that small zero steady state error. So this is the transfer functions of the speed. Okay, I can have an option of maintaining that torque loop, but I have to make sure that it is closed. Yeah, or I can also replace that torque loop with a unity gain here, transfer functions, and then this is just a B plus SJ here. Okay, which is just B plus SJ here. So it's either replace this torque loop with a unity gain, or I can also maintain the torque loop and then close the torque loop. All these files is I will give you, or you can try and look at it later if you are interested. I will pass it to Dr. Tole or Pak Tole later on. Okay, so once we have designed the controller, then you can you have to verify first, because our controller is basically designed based on the linearized model of the system. Because our system, the actual system, is very nonlinear. We know that power electronics converter is a very nonlinear systems, and we just linearize the power electronics converters in order for us to be able to design the controller, the linear controller. So which means that once we have designed the controller based on the linearized model, then we have to make sure that our controllers really work with the actual nonlinear system. This is where you perform the large signal simulations. For example, a large signal simulation consists the actual switching converters and the actual DC motors here, rather than just a model equations that we used before. This is the converter switching, which is using the unipolar switching converter. This is the power electronics, the 4-quadrant power electronics converter based on the MOSFET devices here, or IGBT devices. This is the speed loop, sorry, the torque loop. Okay, the torque loop here, and the speed loop here. Okay, for example, this is the result that I obtained from the file. Okay, this is the yellow one is the reference speed. The blue one is the actual speed of the machine, of the motor, and this is the torque, and this is the current. You can see that the acceleration, the actual speed, is following the reference speed nicely with the acceleration, torque, acceleration and deceleration limited to this maximum torque, and which depends on the maximum current here. Okay, which is limited by that. If you are interested, you can watch my YouTube channel. Just type Nik Rumzi Nik Idris. Then I have discussed in details on how to use these control system design tools, how to model the DC motor, how to model the DC-DC converter, and then how to design the controller using the linear analysis as well as the control system designer in a 3-part YouTube video here. Okay, so let's look at the final part of the example, which is the induction motor drive field-oriented control. Before we can actually look at on the how to develop the model of the FOC drive system, we need to know the modeling of the induction motor. Okay, so I will just give you the equations here. Sebab untuk saya derive the equations, then for my class I will take about 6 to 9 hours to derive these equations, which is the space vector equations of the induction machines, squirrel cage induction machines. Okay, we have the stator voltage equations, the rotor voltage equations, and then the stator flux linkage equations and the rotor flux linkage equations in the general reference frame, which means that a reference frame which can rotate at any speed, okay, at omega g, frequency of omega, angular frequency of omega g, which is represented by that superscript g there. Okay, so Vs is the space vector, or the vector space phasor equations, space phasor of this stator voltage, current, and then the flux linkage space vector, which is represented by that. This is a squirrel cage induction machines, which means that 0 voltage on the rotor voltage equations, but there is an induced voltage here. Okay, this rotor current, and then rotor flux linkage, and the general reference frame speed, and the rotor speed. Which means that kalau saya nak tukar these equations into a stationary frames, then I can just simply set the reference frame equals to 0, the general reference frame equals to 0, then this is going to be the equations which is described in the stationary reference frame fixed to the stator. Okay, again, this is stator voltage equations, the rotor voltage equations, and the stator flux linkage and the rotor flux linkage equations. The torque is given by these equations here, regardless of which reference frame you are writing the torque, the values is going to be the same, right? For example, if it is in the stationary reference frame, then this is given by these equations here. Lm is the mutual inductance, Im is the imaginary part of the product of the stator current vector times the conjugate of the rotor current vector expressed in the stationary reference frames, okay, which is quite complicated now, okay. If you don't have a background in the induction motor modeling, then it is not going to be easy to understand this. But if you have some background on the space vector or the DQ modeling of the induction machines, then this should be no problem for you to understand, right? So if I expand that torque equations into its equivalent D and Q axis, because every vector here can be represented in its DQ axis, okay, or rectangular form, which is a DQ axis, right? So if I expand that torque expressions into a DQ axis, then express the rotor current in terms of the stator current using these two flux linkage equations, then I will end up with these equations here, which is a basic or the fundamental to the field-oriented control, okay? So let's focus on that torque equations. Kalau saya ada, for example, if I draw the vectors, these two vectors, the stator and the rotor flux in the stationary reference frame, then I can resolve this frame, these currents and the rotor flux into its D and Q component in the stationary reference frame, which is shown here, okay? DQ, Q of the stator, Q of the rotor flux, D of the rotor flux, and D of the current here. And in order to control the torque here, it is not going to be easy, because if I control the Q component of the stator current here, then at the same time, I will affect the Q component of the rotor flux, which is on the other side of the equations. All right. And if I control the D component of the stator current, which is the component that we can control, then I will also affect the D component of the rotor flux. Okay. If I control that, then I will affect that, which means that these two components is coupled to each other. Okay. Controlling this will not have a direct, will not have a decoupled control like we have at the DC machines. You know that in DC machines, you can control the torque very quickly by controlling the armature current, because the flux and the current MMF is always, the armature current MMF is always quadrature. There is no magnetic coupling between the two. But for the DC machine, for the induction machines, the torque and the flux component is not 90 degrees, then there will always be a coupling between the flux and the torque components. So what field-oriented control method techniques do is to resolve or to remove that coupling between the torque and the flux component by expressing these quantities in the rotating reference frame, which is fixed to the rotor flux. Okay, so the new axis is fixed to the rotor flux here, which means that the Q component of the rotor flux is going to be equals to 0. And the magnitude of the rotor flux in this D component is going to be equals to the rotor flux itself. Okay, the magnitude of the rotor flux itself, which means that if I go back to these torque equations here and setting psi RQ equals to 0, then I can replace the torque equations with these equations here, which is, if you compare to the DC motor equations, is similar. Okay, because we only have the current, one current to control, which is the armature current, equivalent armature current in the DC motor. And then we'll typically fix the rotor flux, which is the field flux in the DC motor, constant. And by keeping that, by controlling that Q component of the stator current, we will not affect the rotor flux component here, because these are quadrature or 90 degrees or orthogonal to each other. Okay, which means that there is no magnetic coupling between the Q component of the stator current and the rotor flux itself, because of the 90 degrees quadrature or orthogonal between the two. And at the same time, because this, if this rotating frame is expressed in speed which is rotating synchronously with the flux, with the rotor flux, then all the values will be expressed as a DC quantities. Okay, will be expressed or will be obtained as a DC quantities, which further simplify our control. So in order to do that, then we have to know what is the locations of the rotor flux. Okay, what is the locations of the rotor flux? There are two ways to do that. One is to use what we call the indirect FOC by obtaining the locations of the rotor flux based on the reference value. And the other is to use a feedback, which is to calculate the rotor flux position based on the voltage, the current, and the speed of the motor. Okay, so if you are familiar, you probably heard of the indirect FOC and the direct FOC, which comes out from the way on how to obtain these positions of the rotor flux. Let's look at on the FOC, the indirect, very quickly. All right, so the rotor current, the rotor voltage equation here expressed in the general reference frame is first written by removing the rotor current itself using the rotor flux linkage equation, substituting that into the equations here, replacing that, we obtain these equations here. Okay, using these equations here, this is expressed in the reference frame, which is rotating at the rotor flux, right? If you rotate at the rotor flux, which means that, again, as shown by the graph, by the vector before, that the Q component of the rotor flux is equals to 0. The Q component is equal to 0, and the magnitude of the rotor flux in the D component is equals to the magnitude of the rotor flux itself. Okay, jadi I can therefore replace that Q component of the rotor flux. The D component of the rotor flux with the magnitude of the rotor flux. Okay, and then the difference between the speed of the rotor flux and the mechanical speed of the rotor flux of the rotor itself is the slip frequency, right? The slip frequency, which means that now if I resolve these two components, the D and the Q axis components from this equation here, based on this relationship here, then I will end up with two equations, the D components and the Q components. Right? The D components will give you the reference to the Q component or the D component of the stator currents, whereas the Q component will give you the reference to the Q component of the stator currents in the rotating reference frame, as well as it also gives you the slip frequency. All right, so based on that and based on the torque equations, which is derived in the rotating reference frame, then we can derive the reference values for the D component of the stator current, the Q component of the stator current, as well as the slip frequency of the system, because the system is rotating at the synchronous reference frame, which is attached to the rotor flux. So how do we implement that? We have the torque reference. From the torque reference, we generate the three reference, which is the D component of the stator current, the Q component of the stator current, and the slip, which is calculated from these equations here. Okay. And then from there, we generate the reference current in the rotating reference frame. And then in order to implement that, then we have to convert these rotating frames into a stationary reference frame. And in order to do that, we have to know the positions of the rotor. So using the indirect FOC, that position of the rotor is obtained by adding the slip with a measured rotor speed. Okay, you have the slip plus the rotor speed, then you integrate that, and then you get the positions of the rotor flux, which is used to transform the rotating field stator current into a stationary current, and then from there you transform that into a three-phase axis component, and then you implement the current using the current control voltage source inverter, and this is how the indirect FOC is implemented, which means that you have two frame here, the rotating frame on the left hand side and the stationary frame on the right hand side of the block diagram. And how to implement this? I have also actually the name of the file, I can't remember, that I will give you this file as well for you to look at. So this is the power electronic converters that we use. We have a three-phase power, which is we use the uncontrolled rectifier or diode rectifier to generate that DC voltage here. And then we use the three-phase IGBT. That gating signal there to the IGBT there is generated inside that indirect FOC controller. This is the three-phase induction machines. And then this is the feedback, the frictional feedback, okay, the load feedback, which is basically viscous frictions feedback. It depends on the viscous frictions of the system. So if you click that small arrow there, okay, then you will get into this block diagram here, which shows you the algorithms of the indirect FOC. This is the speed reference and the flux reference, which generates the D and Q of the stator current in the rotating frames. And then this is the D and Q current in the stationary frames. This is in the rotating frames, which is transformed using the flux position here, which is obtained by adding the slip obtained from the reference values and the measured rotor speed here. Okay, this is the measured rotor speed. And then the two-phase is then converted to a three-phase current, IA, IB, and IC, which is implemented using the hysteresis current control. Okay, this is the hysteresis current control, which generates that 1, 2, 3, 4, 5, 6 signals there, which is fed back to this IGBT there. Okay, so this is the results, example of the results that we have. This is the speed. I think the reference speed is a square wave speed. So this is the speed response. This is the acceleration torque, deceleration torque, acceleration torque, which is very sharp torque that we have here, which is impossible to obtain using the scalar control unless you use a field order control or any other vector control to get that sharp, nice torque response of the machines. If you zoom to that, then you can see that this is basically a switching, okay, of the torque. And then you have the switching of the, I'm zooming at around 0.63, 0.7, which is around that, I think around that area there. All right. And you can see that, you know, the sequence of the current changes here when the speed changes from positive to negative or from negative to positive here. And the sequence of the stator current also change from ABC to CAB, ABC to ACB, and vice versa. Okay, another method is to use the direct FOC, right? The direct FOC is where you obtain the flux position by calculating based on the feedback of the current and the speed, okay, from the rotor speed voltage equations here. Then you can write down the equations, again substituting the rotor current with the rotor flux linkage equations, and then resolving that into D and Q component. Then you have the D and Q component of the rotor voltage equations expressed using the flux linkage equations. And then from there, you can actually calculate the rotor flux D by integrating, perform a closed loop integral of that, as well as to obtain the Q component of that. And then from there, you can calculate the rotor flux positions based on the magnitude of the D and Q axis. You can also calculate the positions of the rotor, and you can also calculate the magnitude of the rotor flux, right? And the torque can also be calculated from there. So how do we implement that? You have the torque speed reference, and then you have the feedback, the current feedback and the speed feedback, in which you calculate the flux position, the torque. Here, the flux position, which is used to transform the rotating frames into a stationary frames. All right, this is the rotor flux position. And then from the 2 axes, we transform back to the 3 axes. And then from there, we implement the current ABC using the current controlled voltage source inverter. So how do we implement that? Simulate that again using the same power structure here. The power electronic converters remain the same. The difference is only on how to generate that control signal, which is using the direct FOC. If you click that, then you can see that this is basically the algorithm that we use to generate that switching signal here. This is the rotor flux calculator, position calculator, okay, which is used to transform that rotating frames into a stationary frames. And then we use a 2 to 3 phase transformations from DQ to ABC, which is then implemented using the hysteresis current control. This is one of the many ways that you can implement the FOC using the hysteresis. You can also implement using the pulse width modulation current control, or you can also use the predictive current control in order to implement that reference current here. Right? Rather than using the hysteresis or the PWM, you can also use the predictive current control to implement the reference current. So this is the results, which is almost similar to the indirect, except that you probably see a little slight overshoot there in the torque reference because of the feedback. We can improve that by improving on the feedback controller there, because as you can see here, there are 2 PIs that we have to include here. We have to design, which can also be implemented using the fuzzy controller, for example, or some people use the other method of, instead of using the PI control, you can also use other nonlinear controller. All right. So I think that's all. Some examples which I can give you on how to use MATLAB Simulink in the applications of the electrical drive systems. And as I said earlier, I will, if you're interested, then you can obtain these files later on and then look at on there. And then if you have any question on the implementation or on the simulation, then boleh sentiasa tanya saya anytime. All right. So I think I will pass back the session to you.
Terima kasih, Prof.
Ya.
Terima kasih banyak atas materi yang telah disampaikan, luar biasa ya. Ini ada sedikit question and answer, Prof. Bisa dibuka di
chat.
Ini ada dua, ada penanya.
Oke.
Bisa dilihat.
Oke. Soalannya saya tengok di chat box ya.
Di Q&A.
Q&A, sorry. Q&A. All right. I can see from your simulation result, the battery state of charge drops from 100 to 95% for approximately 15 km to off travel distance, if I'm not mistaken, which means the regenerative braking contributes quite well. The energy consumptions in actual commercial electric vehicle operation do not. How do you think that the same energy consumption characteristic can be expected? Yes, you are right, because in my simulation, which is a simple simulation which I use to illustrate the system, the braking is completely 100% regenerative, which means that all the mechanical is basically transformed to the mechanical braking is transformed to the electrical. But of course, in actual, you cannot do that, because the battery will have a limited charging current. You cannot charge, the braking current cannot be used to charge the current, because there is a limited amount of current that can be used to charge the current, which means that the the state of charge is going to be slightly lower than it is supposed to be, 95%. If you consider that the braking is a combination of the electric as well as the mechanical braking. But we are working on that. Actually, we are working on how to improve that by inserting a supercapacitor to the system, because the supercapacitor can absorb the rest of the electrical power, which is not absorbable, or which is not, which is not in which the battery cannot absorb the mechanical energy. The supercapacitor can take care of that. Okay, sebab supercapacitor ni dia.
Sorry, Prof. Bilang, Prof, suaranya. Ya. Mohon maaf ada sedikit gangguan sepertinya dari Prof. Nik Rumzi ini. Mungkin yang lain ada yang mau ditanyakan bisa di share di question and answer.
Is it broken just now? The link putus
Prof.
sikit tadi ya.
Iya.
Okay, alright.
Iya, Prof.
So is that answer the first question?
Ya.
So can I move to the second question now? All right.
I think yes.
Okay. How to approximate the maximum of torque that can be produced using the FOC in the simulation? Or ideally, there should be no limit to the torque to be produced as long as enough current can be supplied to the stator. It depends on the machine. It depends on the machines that you use. You know, the characteristic or the specifications of the machines. For example, in my simulations, I'm assuming that the rated torque is 1 Newton meter, for example. Okay, is it 1 Newton meter based on my simulation just now? I think it is. Hold on, let me check. No, 20 Newton meter. Okay, my machine has the maximum torque of 20 Newton meter. But again, that maximum torque does not necessarily mean the rated torque, because we have discussed earlier, for the machines, you can go beyond the rated torque. Okay, for example, you can go twice as large as the rated torque. If the machine has a rated torque, for example, of 10 Newton meter, then during acceleration for a short time, it is permissible for us to go beyond that 10 Newton meter. Okay, for example, if you buy the electrical drive machines, commercial electrical drives, they will give you the time of how long you can go beyond the rated torque. For example, twice of the rated torque, you can go for 3 minutes, which is possible which is good for faster acceleration, right? So the amount of torque, it will depend during the acceleration, will depend on the specifications of the machines, and it will depend on the thermal capacity of the machines. All right, but to continuously operate, you have to make sure that it is within the ratings of the machines. All right, unless you want during the acceleration, typically we can go as far as, you know, for a servo drive system, you can go, for example, as 8 times as high as the rated currents, because servo motor is designed to have a large thermal capacity, which means that, you know, the current windings can provide a current which is several times of the ratings of the rated currents. All right, so is that answer the question?
I think has been answered the question, Prof.
Yeah.
Maybe,
all right.
Lagi,
Bagaimana jika FOC digunakan pada generator induksi? It is typically used in the wind generator, to use FOC in the wind generator, but it is not actually, I have not actually performed that in my lab. I just use that as for the machine, but it is also possible, using the same concept, we can use the FOC, which is operated as a generator, machine which is operated as a generator, which is typically applied for the wind turbine, which utilizes induction machines, for example. Yeah, it is possible. It is possible. Okay, any other question?
Benar, Prof.
Ya.
Apakah dari teman-teman peserta, apakah ada pertanyaan lagi? Jika sudah tidak ada pertanyaan,
saya tidak pastilah sama ada terlalu cepat ya saya punya presentation ni. Sebab saya have to cover within, sebab contohnya yang induction machines tadilah, saya cover, saya kata dalam 9 jam. 9 jam, jadi saya terpaksa kompreskan ke dalam 30 minit. Jadi you can imagine lah how compressed it is. Dan juga fundamentals of electrical drive tadi pun saya compress lah ya. Biasanya saya sampaikan dalam 3 ataupun 4 jam, tapi saya kompreskan dalam 20 minit. So Jadi memang susah lah untuk paham.
Iya,
Kalau
Prof.
kalau orang yang tiada background lah, tapi kalau orang yang sudah ada background, saya rasa tak menjadi masalah. Oke.
Baiklah, mungkin jika tidak ada pertanyaan lagi, kita cukupkan sampai di sini, nggih, Prof.
Ya, oke.
Oke, terima kasih banyak atas waktu dan ilmu yang telah dibagikan untuk teman-teman semua yang ada di Zoom ini.
Dan saya minta maaf lah kalau susah nak dipaham ya.
Iya, Prof.
Kalau susah nak dipaham. Tapi kalau nak bincang, kalau kita sama-sama bincang, kalau you ada project, kalau siapa-siapa yang ada project yang related pada electrical drive, kalau nak suruh saya involve ataupun kita sama-sama bincang, bila-bila masa kita boleh collaborate ya.
Benar, Prof. Untuk Pak Tole mungkin ada yang mau disampaikan.
Ya, Pak Tole.
Terima kasih banyak Prof Nik.
Baik, Pak. saya tak tahu lah Pak. Bagus ke tak bagus. Terlalu
Bagus
cepat.
sekali lah. Cuma emang cepat sangat lah.
Cepat lah, itulah. Saya perasa memang cepat.
Tapi tak apa lah untuk motivate kita. Nanti next time lah kita boleh discuss yang lagi ini.
Kalau lagi detail, kalau saya boleh ambil satu topik untuk discuss, maknanya sepatutnya FOC itu saya discuss, ataupun DTC ataupun PTC Predictive Torque Control untuk satu session pun.
Ya.
Barulah sebenarnya mencukupi sebab ya. Itulah.
Oke, sekali lagi terima kasih Prof Nik.
Ya, sama-sama.
Cukup, Dil.
Oke, terima kasih semua.
Ya, terima kasih atas waktu dan tempatnya. Untuk teman-teman semua juga, mungkin itu saja dari kami, dari semua host di sini. Mohon maaf jika ada kekurangan. Kita tutup sama-sama acara ini dengan membaca hamdalah. Alhamdulillah.
Alhamdulillah.